Hi everyone. So this is lecture 15, but I'm not going to teach any new material in this lecture. This is the last lecture before midterm number 2. So what I'm going to do is just review null hypothesis testing, and then I'm going to run over a bunch of practice questions that we'll take up in the Zoom meeting on November 11. And then what I'll do is I'll shift over to a little demonstration and I'll show you on my screen what happens when we run statistical tests in R and what that looks like. And this is something that you're going to be doing on homework number 8, which is due also on November 11. Okay, so just a review of null hypothesis testing. I've set up this flow chart to kind of remind you of what it is we're doing. And just remember, this is something that takes a lot of review to really internalize. Okay, so suppose we have this situation where we have this new drug that we've invented and it's supposed to cure nausea, and we want to know, does this drug reduce nausea better than a placebo? Okay, so our null hypothesis is that the drug has no effect on nausea and that there'll be no difference between the treatment group that we give the drug to and the control group that we give the placebo to in terms of the number of vomiting events. Let's say that's how we're measuring nausea. Our main hypothesis is that the drug has an effect on nausea and that the treatment and control groups will differ in terms of the number of vomiting events. Okay, so suppose you run your experiment and you get some data and your data looks something like this. We've got these two box plots here. We've got our people in the placebo group, our people in the drug group, and we're hoping that the drug group is going to have a lower number of bad nausea symptoms, and that's our measurement. We're just going to count the number of vomiting events. But we know that random chance events occur, and we know that just sometimes, because of sampling variation, we might get differences between these two groups that are just due to chance. So the question is this difference real, or is it consistent with sampling error? So in our hypothetical example, suppose we had a difference between our treatment groups of approximately 8 vomiting events. So on average, the people who got our new drug had 8 fewer bad times. Okay, so especially with small sample sizes, we know that we could get differences just by chance pretty easily. So maybe this difference is due to chance alone. So is this difference real, or is it consistent with something we might expect to observe by chance, even if the drug has no effect? So even if the null hypothesis is true. Okay, so to figure that out, we start by assuming that nothing's going on. We assume the null. We assume that the drug is no better than the placebo. And what our software does is it gets the probability distribution of all possible outcomes we could observe in this experiment if the drug had no effect. And this distribution is the null distribution. So this distribution is saying, let's assume the null is true. How likely would it be to get a difference of 0, a difference of 1, a difference of 2, all possible differences between our two groups? And so just a reminder that this step is being done by software. It's being done by your computer. And the exact features of this null distribution will depend on the type of data you're analyzing, the sample size, and the variability or the spread in the data that you're measuring. Okay, so the next thing that happens is we calculate, or our software calculates, how likely it is to get a difference as extreme as we actually observed or more extreme. And this is our p-value. And again, this is done by software. So in our observed data, we got a difference of 8. So the people in the drug group had 8 fewer bad events than the people in the placebo group. And the software calculates the probability of getting that kind of a result if the null was true. And it adds up the probabilities for anything either that extreme or more extreme, and that is our p-value. So if the null was true, that's the probability of getting the data we observed. So next up, we interpret the p-value. If p is small or less than our alpha threshold, that means that it would be unlikely to see the results we did if the drug had no effect, and in that case, we would reject the null hypothesis. But maybe we could get a scenario where the p-value is large and larger than our alpha threshold. That would mean that it would be pretty easy to get the results that we did if the drug had no effect, and in that case, we would fail to reject the null. I think this meme is a nice reminder of what you're supposed to do there. Okay, so finally, we report on the results, and we'd also report things like the effect size, the descriptive statistics, the type of test we ran, the sample size, and the p-value. And then we'd ask new questions. We'd design further studies to address them. So that's what we're doing with the null hypothesis testing approach. Okay, so as some practice for the upcoming midterm, I've set up this flow chart, and what I'm showing here is like the Brightspace course home. So if you scroll down to lectures and videos, under the lecture slides for this week, there's a link to this flowchart PDF, and I'm going to show it on the next slide. What I want you to do is download it and fill out the parts that we've covered so far. So all of the orange boxes on that flowchart are items that you should be able to fill in using the two most recent lectures. There's other boxes on there that are pink. I'll show you what it looks like here. So this is what the flowchart looks like. You should be able to fill in the orange boxes. The pink boxes we're going to cover after midterm number 2, so you won't be able to fill those in yet. Okay, so just a little bit of practice, and we'll take up the answers to these on Zoom. So one of the important things that you have to do, your software doesn't do it for you, is to decide like what type of test should I be using. And so in these examples, I think there are 8 of them. So for each of these 8 examples, these are questions. Think about what would the data look like, and what are we asking here? What type of test could we use to address this question? Would we be using a binomial test or a chi-squared contingency test? So those are both analyses where the dependent variable is categorical. The difference between them is that the binomial test compares a proportion to a specific expected proportion, and the chi-squared test asks whether there is an association between 2 categorical variables. And as another set of practice questions, there's 6 questions here. And for each one, again, think what the data would look like. You can even like draw it in a spreadsheet. And would each of these be analyzed using a binomial test or a one sample t-test? So remember, the difference between those 2 types of tests is, again, the binomial test is for categorical data, the one sample t-test is for numerical data. And so in the binomial test, we're asking, is the proportion different from some expected value? And with the one sample t-test, we're asking, is the mean different from some expected value? All right, so for the last part of this video, I just wanted to quickly show you how you can run things like a binomial test and a chi-squared contingency test in R. And so you should download the assignment number 8 here. And in this assignment, the first page is kind of introduces you to the R statistical platform. And so you can read that. And then down below, starting on the next page, is the actual assignment. And you're taken to, you will be using some data that we've seen before from the CARS 1993 data set, but we're going to run it in this website here called Snippets that lets you run R code in your browser. So it's not the usual way to do that, but I just prefer that for this introductory level course. Instead of having everybody install the software platform on your computer, you can run it in your browser without installing anything. If you do want to install R or R and RStudio, RStudio is a kind of GUI that looks like this, you can do that as well, and you can run the same code as we're running in Snippets. The only difference is you have to actually install the mass package. So that's an option for you as well. Okay, so follow along the instructions in the assignment, and every time you see text that's in these blue shaded boxes, that is example of code that you should highlight, copy, and then select everything in the snippets window and get rid of it and just paste the step from the assignment. And then what you want to do is either click on the run button or hit Command Enter or Control Enter, and that's going to run your code. And then you'll get down below the output that you would get from R. And it's the same kind of output you'd get if you were running an installation of R on your own computer. And in this case, what we did was we just loaded up the mass package, and then we just printed the data set so you can inspect it. And it's got quite a few columns, so it continues down for a lot of rows. Okay, so so one of the first things I want to show you to do, so I'm just going to get rid of that, is to show you how to run a binomial test, and that's going to show up a little bit later in the assignment. So I'm just going to zoom in a little bit to make sure you can see on the video. And the way we run a binomial test is with the function binom.test, and then we've got a pair of brackets, and in the brackets we have to give it 3 values. The first value is the number of objects in our sample that met some criteria. Like, let's say we're studying babies that were born in Ottawa, and we have 100 babies, and let's say 25 of them were male, and so we want to know if this ratio of 25 males to 75 females is significantly different from the expected 50-50 ratio. So we'd write binom test 25, 100, that's our sample size, and then the last number we have to supply the function is our expected proportion. So that's going to be, let's say 0.5. And if we hit the run button, it takes a moment, and then we can scroll down and we get the output from our binomial test. So it includes a descriptive statistic. It calculated the proportion that were male. In this case, it was 25%. And our p-value, or our sample size, is right here. And our p-value here is this number here, which looks really weird, but it's actually representing a really, really small number. This is telling you that the p-value is 5.636 times 10 to the power of -7. So that's a very small value. It's definitely less than 0.05. And so if, as you're working through the assignment, there's a point at which you need to run a binomial test, and that's right here. And I'll just zoom in a bit. And so what you'll be doing is copying and pasting that over, but it won't work unless you replace the x and the n with the actual values that the instructions tell you to use. Okay. Now we could have a different scenario, like we could have a sample of, let's say, just 10 babies, and let's say 3 of them are male, so that's a greater proportion. It's 30% instead of 25%. But if we run this test, you'll notice that we, and our p-value is right here, and then we've got our descriptive statistic down here, but we've got a p-value now of 0.34, which is quite a lot larger. So in this small sample size, even though we got only 30% male babies in this sample, it's very easy to get a sample like that. It's very probable to get a sample like that if the null hypothesis here was true. All right. Okay, so that's how we run a binomial test. I want to just very briefly show you how to run a chi-squared test. And I'm just going to pull an example from the CARS 1993 data that we use in the assignment. And I'm going to copy this text here, and I'll just highlight everything and replace it. So in this example in the assignment, we set up this new variable in the CARS 93 data set that just represents whether or not a car has any airbags. So it's this binary variable that we create that's either like airbag or no airbag. And what I want to do is run a chi-square test, and I want to look at whether that variable, airbags or not, is associated with a car's country of origin. So I'm going to first make a table. So I'm calling up the CARS 93 data set. I'm going to use my new variable that I created, and I'm going to look at origin. So I've typed in table, and that's going to make a contingency table. So if I click run, it's going to run everything that I have entered there, and here's our contingency table with our new variable, airbag or no airbag, and we've got the counts of cars in each of these possible combinations of these two variables. Now I just want to show you something. Because R is this command line platform, it does not tolerate any typos, any differences in capitalization or anything like that. So if I had accidentally used a lowercase c here, right, and if I try to run that, I'm going to get an error message because there's nothing in our environment, in the R environment that we've created, that is called lowercase c Cars 93. The data set that we have that comes with this package, its name starts with a capital C. So when I type it in as a lowercase c by accident, the computer doesn't know what to do with that. So everything has to be typed correctly, including the capitalization for things to run. Okay, so we already ran that. And so let's make a bar graph of that information. So if I just copy this text, and I'm actually just going to change this to a tilde. This is kind of extra from the assignment, but I just wanted to show you how you can make a mosaic plot, right? So this is the same information shown in the contingency table, but it's a little bit easier to interpret when it's shown as a graph, because we can very easily visualize, okay, in the American-made car category, there's like a slightly higher proportion that have airbags, but it's pretty similar when we're comparing the non-American-made and the American-made category. Okay, and lastly, we can run a chi-square test. And the way we do that is with this function chi_sq.test, and then we have to enclose some information in brackets there, and we can either just tell it the two columns from the Cars 1993 data frame that we want to use, or we could even feed it this table, and it will should run the test either way. So and so what happens with snippets is that it kind of prints all of the non-plotting stuff first, and then you get like any plotting stuff you asked for at the bottom. So our test result is presented right here before our graph. And so we get our chi-squared statistic, a degrees of freedom, and then we get our p-value. And so the p-value here, 0.65, is greater than our alpha threshold of 0.05. So we fail to reject the null hypothesis that there's no association between these two variables, a car's origin and whether or not it has airbags. All right. By the way, we can also check here in our contingency table that this was reasonable to run a chi-square test. We had like all the values here were fairly large. We're well above 5, so that's good. Okay, so the last thing I wanted to show you how to do was just a t-test, which is something that's covered in the latest lectures this week. And so t-tests are useful for numerical variables. So let's make a graph and run a t-test to look at whether a car's price was related to whether it was an American origin or not. And to run a t-test of the same information, the function is just t.test, and we're going to specify. We want to know whether price is associated with origin. So I think that's going to work. Let's find out. So we click run. And so again, we get the output in a different order than we put in because the plots always end up at the bottom. So here's our box plot showing the distribution of car prices from 1993. These are in thousands of dollars. So we can see how it's pretty like similar distributions. It looks like some of the non-American made cars include some of the most expensive ones. And let's see if the t-test, what the output of the test was. So we've got descriptive statistics down here with the means of the mean price for these two different groups. And so this is a paired t-test, and we've got our t-statistic here, and we've got our p-value here of 0.34. It's pretty large, so we fail to reject the null hypothesis that there's no significant difference between these the prices for these two car origins. Okay, so that's it, and I'll see you in Zoom.